We start with a cinematic scene of an astronaut on horseback, but looking closer, the image shatters, revealing a construction of glowing, chaotic TV static. It is tempting to think an AI model creates these frames by mimicking a human artist holding a digital brush, but the system is operating on a different logic entirely. Every AI-generated image begins as a grid of random pixels. This is absolute mathematical noise, a blank coordinate representing a state of maximum entropy. This digital noise has a physical equivalent, Brownian motion. It operates just like dust particles colliding and diffusing when suspended in a light beam. Resolving an image from this chaos is a physics problem. The system must find a mathematical way to reverse the natural physical decay of information. To master this, researchers simulate the destruction. They take a clean training image, systematically add noise, until it is completely obliterated. The AI observes this to learn vector fields, the mathematical paths pixels took as they decayed. By learning the exact trajectory of that decay, the model runs the clock backwards, pushing random dots along their previous paths to reconstruct the original structure. A simple step-by-step cleanup isn't enough. The AI must predict the total noise added across the whole process, while simultaneously injecting a small amount of new random noise. This extra randomness keeps the pixels from collapsing into a blurry, indistinct average. This reverse diffusion provides the mathematical engine needed to turn chaos into structure. But the system still lacks a way to dictate which specific structure it should form. Now that the AI can build a structure, we face a navigational challenge. How do we tell it to build a city at night instead of a cat? This is where CLIP comes in. It's a shared mathematical map, where words and visuals exist as coordinates in a high-dimensional space. Typing a prompt translates your words into a specific mathematical coordinate inside this territory. During conditioning, the diffusion model uses this coordinate as a directional guide, pointing the random noise toward that requested destination. However, this directional pull is often too weak. The broad average of the entire training dataset can overpower the prompt, resulting in generic images that ignore the specific details you asked for. A coordinate alone isn't sufficient. To reach the true destination, the AI must actively push away from the irrelevant noise. To solve the gravity problem, researchers use a technique called classifier-free guidance. The AI calculates paths for generic noise and your prompt, then subtracts the generic path, forcefully amplifying your signal. This shortcut avoids hundreds of random, bumpy steps, calculating a smooth, rapid trajectory directly to the exact data distribution. Combining a linguistic map with this deterministic guidance creates a tool capable of resolving highly specific concepts out of pure static in seconds. With still images solved, the next frontier is expanding this diffusion engine into the dimension of time. Video generation requires more than just a sequence of separate images. The engine must calculate how those physical vector fields shift and evolve frame by frame. The AI maintains consistency by ensuring that each pixel's movement is mathematically tethered to its neighbors and the frames that came before it. By calculating these dependencies, the system preserves the structural logic of objects as they move through time. This is the full pipeline. Human text becomes a mathematical coordinate, which guides a reverse diffusion engine, amplified by guidance, and finally expanded into a temporal sequence. Ultimately, these models do not create through imagination. They function as a calculated mathematical vector field, literally resolving absolute order out of total randomness.